got the LittleMachineShop.com model 5100 mini lathe. This is their 7x16 version of the mini lathe. And as I've talked about in some of my other videos, the 7-inch or 7 part of the name refers to the largest diameter workpiece that you can turn or rotate and work on. And the 16-inch refers to the distance between centers, or basically the distance from the spindle to the tailstock. Now the mini lathes come in, I think, 4 different sizes, the smallest being nominally 7x10, which is about half the length of this one, and then the 7x12, which is 2 inches longer, 7x14, which is another 2 inches longer, and this one, which is the 7x16, which is the longest model that's currently available and that ever has been available. Now there is one other vendor that sells a 7x16 model, which is Micromark, and I've had their 7x16 over here on the other side of my workbench for quite a few years. Been very happy with it. So this is a relatively new model. It's been around for a few months, and I thought it would be good to take a look at it and see how it compares to the others. The vital statistics for the lathe can be found here on this chart on the front panel here. We'll go through those briefly, but the swing over the bed, as we talked about, is rated 7.1 inches. Swing over the saddle is 4.3 inches, and that's if you're working on a long workpiece that has to reach all the way from end to end. It has to cross over the saddle, so the saddle limits the diameter of the longest workpiece that has to extend over that to 4.3 inches. Now the distance between centers, as we talked about, is 16.1. And of course these are all actually made to metric specs, so the inch equivalents are shown here, but the actual specs from the factory are the metric ones if you're interested in those, but they're all right here. Cross slide travel, that's I think self-evident. Hole through the spindle is an important one. That's the largest diameter workpiece that can fit through the spindle. So if you're working on a long rod that may be longer than the lathe itself, the largest diameter that you can pass through the spindle is a little over 3/4 of an inch. So I would say nominally 3/4 of an inch. And your spindle taper is Morse taper number 3, tailstock taper Morse taper number 2. This one's real important, is the spindle motor. This one has a 500-watt motor, which is quite powerful for a lathe in this size class, and we'll get into that. And the speed is from 100 to 2500 RPM, and it's all in one range. Some mini lathes have 2 ranges, a high and a low, that's determined by a gear shift, but this one, because it has the brushless DC motor, has the entire range in one pass. So it runs on standard house US type house current, 120 volts at 60 hertz. You probably need a 20 amp circuit, but it'll probably run fine on a 15 amp if that's all you have, as long as it's got a 3-prong outlet. And it cuts threads, both metric and SAE threads, and we'll talk about that as we get further into the review. It's a pretty hefty little machine, 110 pounds or 50 kilograms, so you almost certainly will need some help if you get one and need to set it up in your shop. You'll need a helper to lift it up and get it set up. So let's move on. On this model of the mini lathe, the controls are up here on the top of the panel. On some others, they are on a sloping part of the panel that comes down here. But we'll look at these and see what we've got. The primary control here is the on-off power button. The green button turns the lathe on, and you just depress that, and assuming we have power here, let's see, we do. And then I turn the speed control knob. You can probably hear it rumbling there in the background. And to turn the lathe off, you press the red button here. The red button also serves as an emergency stop. It's raised up a little bit above the green button, so if something's not working just right, you can mash that down with the palm of your hand or your finger or whatever. But it just makes it easier to stop the lathe if you have to do that quickly in response to some problem. Maybe you didn't get your workpiece chucked up quite tightly enough in the chuck and it's starting to work loose. So that's how that works. The little power indicator here, or pilot light, glows green when the green power button is turned on. It's a little bit hard to see here with the lighting that I have, and it's pretty dim in any case, but I can tell when it's on. Now here we have the forward and reverse switch. An interesting property of this version of the lathe, and many of the newer models of the lathe made in the last 4 or 5 years have a really smart motor speed controller. And when I say smart, what I mean by that is if you switch this into reverse, it automatically slows the chuck down, comes to a complete stop, and runs it in the reverse direction. So let's try that again. I'll bring the chuck into view here, and we'll switch it from reverse to forward. That can be very handy if you're doing a tapping operation where you need to back the tap out. You can run the tap in and then just flip the reverse switch, back it out to clear the chips, flip it again and run it through for a second pass, flip it back to reverse and draw your tap all the way out. Big time saver when you're doing tapping, which is a fairly frequent operation, at least in my shop. So I like that. The other controls here, the fault light indicates that you have an overload condition of some sort, and that can occur, for example, if you take too deep a cut. If you dig the tool in and you're working, for example, on a 4 or 5 inch diameter workpiece, which has a fairly long, or a lot of leverage on the tool because of its large diameter. If you try to take too deep a cut, let's say a 1/4 inch deep cut, there's not going to be enough power for the motor to make that cut, and to avoid overloading the motor, the circuitry will detect the overload condition, stop the motor, and set the fault light. To correct that, you can I think you just turn the power off and then back on. It's different on different models of the lathe. Some versions of the lathe have a click switch on the speed control, and you can reset it by clicking into the 0 position. But on this lathe, this model of lathe, there is no click stop here. So I think in order to reset a fault condition, you probably have to power it off and power it back on. We'll try to test that later by inducing a fault condition and see what the story is on that. There is a fuse here, and you may occasionally have to replace the fuse if one blows, so it's good to keep a few spares on hand, and you can buy inexpensive collections of them on eBay is what I do, and get a lifetime supply for a few dollars. But on the newer lathes, because of the smart controller, it's actually fairly rare to blow a fuse. In the old days it was pretty common before they had the smart speed controller. But since the smart speed controller detects and corrects or acts on most of the overload conditions, you'll probably rarely blow a fuse on these newer model lathes. Now up here we have a little socket, and this is intended for a plug-in optional tachometer. And let me get that and I'll show you how that looks. I've got the tachometer in place here. It has some magnets on the back. I just have it temporarily held in place here on this casting, headstock casting. But if you're going to set it up permanently, you'd probably want to put some cable ties here and make sure this cable's out of the way of the rotating chuck, of course, for safety. But I haven't attempted to do that right now. And of course this painted surface doesn't really grip too well with the magnets. But I did want to put it in this position for the demonstration because it makes it easier to see in this particular angle. So as I turn the speed control knob up, you can see that the tachometer starts to read. Let me zoom in on that a little bit. Now this seems like a good time to talk about another thing. You may be able to see here that as I spun up the chuck, really for the first time on this lathe, it's spraying oil out, and that's pretty normal. The chuck will have some oil in it from the factory, and I may have even had a little oil. I don't think so on this one, but as you speed it up, that oil's going to spin off and get all over everything that happens to be in the pathway there. So just be aware of that when you turn your lathe on for the first time. You may want to put some cardboard in front of or in back of the chuck to keep that spray from getting all over the place. After you run it for a while, particularly as you run it up to 2500 RPM, centrifugal force will spread all that oil out of there, spin the oil out, and that ceases to be a problem after an hour or two of use. But anytime you might add a little oil to there just to keep it moving smoothly, you need to go through that process again. Alright, well, back to the tachometer. I've got the power turned off now. I'm going to turn it back on, and you can see it comes up at the zero, all zeros, and then as we speed it up, we slow it down, and it reaches to the nearest 10 RPM. Now, just a word on that, the speeds at which you turn items in the lathe are actually pretty flexible, or that is, there's a lot of latitude, and you don't have to worry about having it exactly at 840 RPM or 850 RPM. For most of the work you do in the home shop, there's a latitude of probably plus or minus 20% or more from the optimal speed that's used in industrial settings. So in fact, you don't really even need the tach. It's nice to have, and particularly when you're starting out, it'll give you a good sense of how different materials behave when you turn them at different speeds. But you can quickly gain that knowledge just through listening and watching. So if you don't have the money to buy the tach, don't worry about that. It's nice to have, but it's not essential. And if you keep in mind that for the first 100 years of lathe history, there were no tachs, and the guys got along just fine. There's another feature of the switch that isn't obvious just from looking at it, and that is that it has a built-in overload protection, or at least it has a built-in relay that will cut off the power during an overload condition. So if an overload occurs, the circuitry inside the power supply will detect that, and it will cut off power to the motor, and it will cause the power switch to actually reset itself. So when you press the off button here, you can hear there's a little click, and the power light goes out. Similarly, if you're working along and you have the power on and you overload the lathe in some way, the power switch will actually click off like that, and in order to restart the lathe, you have to push the green button once again. So the purpose of that is twofold. One is to prevent overloading the motor and causing possible damage, and also avoids blowing the fuse. At least 99% of the time it does. And the second thing is that it protects you in the event of a power failure. So if power to your lathe is cut off, say due to a circuit breaker that pops or an electrical storm in the area or something, the circuitry will cause the power to cut off, so that when the power comes back on, the lathe won't start up and possibly be rapidly spinning from whatever speed you left it at when the power interruption occurred. While we're on the subject of power failures, one thing I always like to mention is it's a good idea to have some power fail lighting in your shop. In fact, I strongly recommend it. These are some low cost, I think they're maybe $8 each, lights. I got a couple of these, and they have a little outlet prong here. You just plug them into any available outlet, and they stay charged all the time. But if a power failure occurs, the light comes on. You can use it either as a flashlight or just this emergency lighting here with 3 white LEDs, and there's a switch to select which of the 2 lighting modes you want. So that's one mode, and that's the other mode. And you can also use it just as a handy flashlight, and you can retract these prongs so they're not in the way when you're using it as a flashlight. So these are a great idea, so that if you're working with any kind of power tool and the power goes out, you don't suddenly find yourself in complete darkness fumbling around trying to figure out what to do, possibly while a power tool is still spinning down from whatever operation it was doing. Looking now at the back side of the lathe, the back of the headstock, there's a few features I wanted to point out. This first one here is the switch for the chuck guard interlock. This plastic shield folds down over the chuck, and if you lift that shield, it interacts with this switch, which cuts off power to the motor so that the spindle cannot start up as long as this safety guard is in the raised position. When you lower it back down, it triggers a switch and a relay in here so that now the lathe will operate normally. And down below here, we'll take a look inside here in a minute, but this is the cover for the motor. And over here we have the lead screw directional lever, and it has 3 positions. It has 3 detents that are in this block here, and to move the handle you pull firmly out on the knurled surface. You have to pull this handle out, then you can raise it or lower it to one of 3 positions. The middle position is neutral, and when the lever is in that position, the lead screw will not rotate. And we'll get around to the other side and look at that in action a little later in the video. But when this is on the raised position, that gives you so-called left feed, which is the normal feeding direction towards the headstock. And when it's in the lower position, it gives you right feed, which feeds or moves the carriage away from the headstock when the chuck is rotating in the forward direction. So there's a couple of possibilities there that are handy when you're doing threading or reverse threading, cutting a left-hand thread, for example. And we'll talk about all of that later in the video. Alright, well, this is the so-called brushless style motor, and as you can probably see, it's a completely sealed unit. There's virtually no maintenance required on it. There are no bearings to adjust, there are no oil ports to worry about, and there are no brushes to deal with because it's a brushless motor. Look up on Wikipedia if you're interested in brushless motors and how they differ from conventional DC motors. But basically, the armature is isolated from the permanent magnets that make it go, and the coil magnets are pulsed by the electronic power supply in such a way that the shifting phase applies power to the armature. And because of that, there's no physical contact between the rotating armature and the rest of the motor other than in the bearings, and therefore it generates very high torque and is very low maintenance. In fact, it runs so cool that it doesn't even require a cooling fan. It's cooled entirely by convection and conduction through this aluminum extrusion that forms the motor mount or motor housing. Okay, looking at what would normally be the left end of the lathe, if it were turned around in its normal operating direction, you can probably see here this is the pulley for the drive motor, and there's a rubber toothed belt that engages with that. Then it runs up behind this plate here to drive the spindle. And I'll remove this plate so we can get a better look at how that all works. Okay, now we're looking at the left end of the lathe. I've got the gearbox cover removed so we can get access here. And I'm just going to remove these 2 socket head cap screws here so that I can lift off this gear plate and show you the drive mechanism underneath there. And then we'll take a closer look at this. So that should just lift off, and there it goes. Alright, with that removed now, you can see the drive belt. Let me move in a little closer here, give you a better look at that. But you can see the drive belt runs directly from the motor shaft to the spindle, so there are no intervening gears, just these 2 cogs for the drive belt. That has a couple of benefits. One is that it's obviously mechanically very simple. Essentially, about the only thing that can go wrong there is if the belt is loose and slips over the cogs a little bit, which is easy to adjust. You just loosen these bolts down here and 2 on the other side that are hidden behind this gear. Then you can push the motor up or down. You may need a screwdriver or something to apply a little leverage, hold it in place. And when the belt is tight, you just retighten those screws, and that should take care of that. Now the belts do stretch a little bit when they're new, but once they're broken in, they tend to be pretty stable and rarely need adjustment for tension. Now on the mini lathes that have what I like to call the classic style motor, which is the brush type motor, instead of the belt running up here to the spindle, it runs to another shaft that's down below here, and there's a cogged wheel on that shaft, and then internally there are some gears that actually drive the spindle. So this arrangement is much simpler, and it eliminates those internal gears altogether, which is good for several reasons. One is you get direct power transfer from the motor to the spindle, so it's more efficient. Number 2, those gears inside the head actually add a fair amount of noise to the whole driving train, and this belt drive is actually quite a lot quieter than the old gear drive type system. And third, there's not a whole lot that can go wrong because there's just this belt is the only moving part other than the two rotating shafts themselves. So for all those reasons, the brushless type motor with this direct belt drive is the top of the line. It is more expensive, and that's the trade-off, is that I don't know what the difference in price, but it's probably around $200 more to get the brushless type motor than a similar machine with the older style motor. I'm getting ready to put the gear plate back in place here. I did want to make a comment. I'll just drop the screw there. The adjustment of this, or the alignment of it, can get kind of finicky. At least on the older lathes it did, and I haven't tried it on this one. But it used to be that the location of these two holes was very, had to be just right. If the plate was tilted or shifted just a little bit, it could be enough so that these idler gears here wouldn't mesh properly, and therefore the lead screw didn't always go into gear or go out of gear when it should, or sometimes you just get sort of a rattling noise from these two gears here. So we'll see when I put this back whether that occurs or not. Alright, well, I just put the plate back in place and just tried it out here. The lead screw selector knob here is in the neutral position right now. So the lead screw does not turn. These idler gears here are not engaged, and they are what ultimately drives the lead screw through this gear train here. Ultimately turns this shaft, which in fact is the lead screw shaft. So with that in the neutral position, it's relatively quiet other than the belt noise, because these gears aren't moving. Now if I raise this selector level to the upper detent, you can see it engages this upper white gear here, and now the gears are turning. Now if you operate without the safety cover in place, obviously you've got to be very careful not to get a rag or a shirt sleeve or anything else near these rotating gears. So when you're actually using the lathe, you should always keep that safety cover in place so that nothing gets snagged in these gears and causes a serious problem. Yeah, and if I lower this down to the lower detent, the gears turn in the opposite direction. And that sounds like it's not engaging quite the way it should. Yeah, I may need to tweak this. This is what I was talking about earlier. If you remove this plate, and there really isn't any reason why you should remove the plate. I just did that to illustrate how the belt drive works. No, I'm not going to fool with that now, but sometimes you'll get a little clicking noise there if it's not lined up just right. But we'll put it back in the neutral position. Oops, didn't get it quite in the notch there, I guess. It can be difficult sometimes to feel that notch, and particularly when you're working from the front of the lathe, you have to kind of reach back here. That's another reason you should have the safety cover in place. But you have to reach back to get this detent knob here, and it's fairly strong spring on it, a little bit difficult to get at, but you get used to it. Fortunately, you don't have to change it very often. In fact, 90% of the time I leave it in the upper position, so it's driving the lead screw in the forward direction. Sometimes if I don't need the lead screw and I just want the reduced noise level, I'll stick it down in the neutral position. There we go. So let's get that cover back on, and then we'll move on. And we'll come back later and talk about these change gears and how they're used for threading.